Hello, everyone, and welcome to this session, which is a deep dive on AWS Trainium and AWS Inferentia. My name is Shruti Koparkar, and I am the product marketing lead for all things AI ML acceleration. I sit in the EC2 product marketing team, and I'm joined by Matt. Matt, can you introduce yourself?
Yeah, hi everyone. My name is Matt McLean, and I lead the solution architecture team that's part of the Annapurna ML group. So my team essentially help customers onboard their training or inference workloads onto our custom-made silicon for machine learning.
Awesome. So, this morning we heard from Nafa and Gary about the various innovations and design considerations that go into building silicon from the ground up. And then we heard from Gadi and Chetan about the specific use cases that are supported on our ML silicon, Trainium and Inferentia, about our work with our partners. And we also saw a really great demo of the server and how it's not just about the silicon, but also building the server, the data center, the software. Now, this particular session is intended to be a deep dive on the generative AI specific innovations in Trainium and Inferentia. And while generative AI has become a dinner table conversation for all of us, and many are familiar with the term, it always helps to start with the basics. So let's start with that. What is generative AI?
Sure. So generative AI refers to a specific type of artificial intelligence that generates new content based on patterns it's learned from training data. So the content can be generated in various forms, such as text, voice, images, or even videos. So in this example, we've seen multiple AI assistants which generate text in a conversational manner. So you might have heard of ChatGPT from OpenAI or Claude from Anthropic. We've also seen the Stable Diffusion models from Stability.ai or Firefly from Adobe, which generate really beautiful images based on a text prompt. Or even Runway ML, who have developed models such as Gen 1 and Gen 2 that generate videos that comes from text, images, or even other video clips.
Yeah, I mean, it's really amazing how far we've come in this field of deep learning. I remember back when I was in grad school, we were using convolutional neural networks to, say, classify images of cats versus dogs. But now these generative AI models are generating photorealistic images. They are, writing poetry. I have read haikus written by AI. So it's quite amazing. So generative AI is still a form of deep learning. So it does involve training the models and then deploying them for inference. But with these new foundational models, like large language models, customers have another option, which is to fine-tune these models instead of training them from scratch. Can you talk to us a little bit about what are foundational models and this option of fine-tuning?
Yeah, so foundational models, they're trained on a very broad data set, typically gathered from the entire internet. So these could be sources such as Wikipedia, Common Crawl, GitHub, books, academic papers, amongst others. So these models are called foundational models because they can be adapted or fine-tuned to a wide array of downstream applications, such as building a chatbot, maybe a translation tool, or even like a code companion. So in a sense, these models serve as a foundation for many AI-based applications. So a type of foundation model, or as a large language model, or LLM for short. And this is basically trained on vast amounts of text data. And these LLMs are built from a large transformer-based neural network. And they can typically have hundreds of billions of parameters. So in order to build one of these downstream applications, such as a code companion or an AI assistant, often customers will need to fine-tune this foundational model via a small set of human-based examples. And we call this supervised fine-tuning.
Right, so the bulk of the learning happens in that pre-training phase, and then during fine-tuning, you're making small adjustments to your model so that it is suitable for your specific downstream use case, such as chatbots or any sort of conversational agents, so on and so forth. Now, how long does it take to fine-tune versus pre-train?
Yeah, so fine-tuning is much faster than pre-training, and that's actually quite important. So one of the main benefits of these foundational models is that you train them once in a very compute-intensive pre-training phase, but then you can fine-tune them at a fraction of the compute demand for a set of downstream tasks.
Right, so you said a very compute-intensive pre-training phase. How compute intensive is this pre-training? Can you give us a sense of what that is?
Yeah, so it is model dependent, but we typically pre-train foundational models on thousands or even tens of thousands of Trainium devices, while fine-tuning can often be done just with a few tens of devices. So to support efficient pre-training, we've built the Trainium Ultra clusters, and they can support more than 30,000 Trainium devices. And that gives you a total of 6 exaflops of compute capacity and up to 3 petabit of non-blocking EFA network bandwidth. So this enables our customers to train these super large models faster than ever before, while trying to keep costs under control. In fact, some of our customers are seeing 40% lower cost to perform these pre-training of their LLMs.
Right. So you mentioned these Trainium-based EC2 ultra clusters, and these are ultra clusters of Trainium-based EC2 TRN1 instances that have been purpose-built for LLM and generative AI training. And as you said, customers can use these to train models with hundreds of billions of parameters while keeping costs under control. Now, what are some of the other capabilities that enable this sort of scale and price performance?
Yeah, sure. So let's talk about the specifics of the instances. So Trainium is available through 2 different instance types, the TRN1 and the TRN1N. So both of these instances are incredible compute platforms, and they support a wider variety of data types, including 3 petaflops of bfloat16 performance and 6 petaflops of int8 performance. So TRN1 and TRN1N come with 512 gigabytes of high bandwidth memory, or HBM for short, and 13 terabytes a second of HBM memory bandwidth. So we've also coupled our TRN1 instance with 800 gigabits per second of EFA network bandwidth, and our TRN1N with double that, so you get 1600 or 1.6 terabits per second of bandwidth. And this really allows for efficient scaling of thousands of devices in a single training cluster. So all of this is available on demand with our best-in-class power and cost efficiency.
Right. These models are so huge, like we said, hundreds of billions of parameters, and they're also trained on petabits of data. So having that large accelerator memory with very fast memory bandwidth is critical. And then also, as you said, for distributed training, where the training is distributed across multiple servers and scaled, we need the really fast networking bandwidth. So we've really packed a lot of innovation into these TRN1 instances. Now, one thing I noticed was that when you talked about the compute performance for TRN1, you talked about it in terms of 2 different data types, and you also said that we support a wide range of data types. Can you talk a little bit about what are data types and why is it important to support so many different?
Yeah, so in machine learning, the different data types are utilized to represent numerical values with varying levels of precision. So the choice of data type is really important as it affects the computational efficiency, the memory usage, and also the accuracy of our models. So commonly used data types in machine learning include floating point 32 or FP32, and this uses 32 bits to represent a floating point number, and it's widely used for training deep learning models. Another is floating point 16 or FP16. This one uses 16 bits and offers reduced precision, but consumes less memory and enables faster computations. bfloat16 is another 16-bit data type. This provides a compromise between the range of values and the memory efficiency, and it's commonly used in training LLMs. Integer 8 or int8 is an 8-bit integer type, and it's used for quantization purposes, so it reduces even further memory usage and accelerates the computations. So additionally, we also have support for TF32, and there are plans to introduce support for configurable FP8. So this is a new data type that some customers are starting to use for training large language models.
I really see this as an extension of the flexibility and choice that we offer with Amazon EC2. Amazon EC2 is the broadest and deepest compute portfolio, and similar to that, this choice of a wide range of data types is really critical so that our developers can choose the right data type based on their use case. Are they training versus are they doing inference? What are their performance and accuracy goals? What is the kind of memory footprint they want? So yes, that flexibility and choice is just so critical. Now, let's switch gears a little bit and talk about model deployment. I really see like the magic is built during the training and the pre-training or fine-tuning phase, but it's experienced by our end users or by our customers' end users when the model is deployed.
Yeah, so when we're thinking about deploying models, it's really important that we think about the end use case when we're training and deploying these models. So a successful model needs to be deployed at scale, right? Often serving thousands or even millions of requests per second. So this needs to be done in a performant, power efficient, and cost-effective manner. So this is to achieve, the expectations of the user, often of that real-time experience, at an acceptable cost per inference.
Right. And AWS Inferentia 2-based EC2 Inf2 instances are purpose-built for just that, LLM inference at scale while keeping costs under control. And what better way of sort of seeing that real-time performance and the price performance than to see Inf2 in action? I know you have a really fun demo for us, Matt.
I do indeed. So today I'm going to share with you a demo of the Stable Diffusion model. That's the model that I mentioned earlier. So it's a way of essentially generating beautiful images based on a text prompt. So here we have Stable Diffusion 1.5 running on an AWS Inferentia 2-based instance. So what we need to do is essentially feed in a text prompt and we'll generate an image for us. So here we can see the web demo. We can pull up for example, here is a prompt. My daughter is a big fan of Frozen, and Elsa is her favorite character. So I've chosen this as the text prompt today. So all we need to do is click Generate. And on the Inferentia 2 device, we're actually now generating an image of Elsa. So there you go.
Wow.
What do you think?
So, no, this is great. So this is an original creation, like doesn't exist anywhere. This was just created.
It's never been created before, and actually to prove that, let's click Generate again and create a similar image of Elsa. There
awesome.
You go.
That's great. What about other princesses?
Yeah, so do you have a favorite, Shruti?
Well, Elsa wasn't around when I was growing up, but Snow White is a classic.
Snow White? Okay, well let's change our input prompt to Snow White and see what the model's going to generate. So we've just changed it there. And we'll click Generate. There we go.
That's pretty neat. Let's try some other prompts, like not princesses, something else.
Okay, so I've also have some other examples. So let's pull up a portrait of a coal miner in the style of the Greg Rutalski. So let's see what this one generates.
Oh, wow. So this is in the style of the painter.
Exactly.
Right.
It's a portrait of coal miner in the style of that particular painter, exactly.
That's really cool. Now, how, I saw that it was like pretty quick. How long did it take to generate an image?
Yeah, so you can see on the screen here, we're actually also showing the elapsed time. So that's the time it's taken to generate. So it's taken about 2.5 seconds to generate this Stable Diffusion model, which is really sort of, great performance for generating these Stable Diffusion images.
Yeah, and I see you have some cost approximation or rather estimation there as well.
Yeah, so we've also estimated essentially what it would cost to generate 1,000 images. So using the on-demand Inf2 extra large, we can generate 1,000 images for the cost of about 50 cents, which is pretty amazing.
And you can save even more if you use EC2,
exactly.
And Inf2 is available on EC2 Spot. And looks like it's 16 cents for.
Exactly. So that's the great thing. So Inferentia 2 is available via Spot. So yeah, it's even cheaper. So if you want to save costs even further, then this is a great option to choose.
That is so amazing, especially important for inference, the great price performance. Because as you deploy generative AI applications at scale and you have more and more end users, you're doing inference that much more frequently, and your inference costs really start to skyrocket. So having options like Inferentia 2 to keep those costs under control while delivering real-time performance is just so critical. Now, one thing I was curious about, how do I know that this is running on Inf2 right now?
Great question. So we can actually show one of the tools we have available in the Neuron SDK. So that is a tool called Neuron Top. So this is a way for you to essentially check the utilization of the accelerators running on this particular instance. So here you can see at the bottom of my screen, we have this neuron top running. So it's showing 2 neuron cores. So on the Inf2 8 extra large, we have 1 device, and each device has 2 cores. And we can see the utilization of each core from 0 to 100%. So when we actually go back to our demo and click Generate again, you should be able to see that the utilization will change. And you can see here it goes up to 97%.
Yep, I just saw that go up to 97.
During that time. And
why don't we do it one more time so
Sure.
our audience can catch it? That's awesome. You know, this is such a fun demo, and I'd love to keep playing, but we have to move on. Are there any similarities between inference and training, especially in the context of generative AI, where these models are so big?
Yeah, for sure, there are similarities. Before the era of large language models, one of the main differences was that inference was mainly done on a single device, while training was often done in a cluster of devices or even using an entire data center. But now in the era of LLMs, this is no longer true. Because these LLMs are so big that they actually don't fit into a single device anymore. So for example, you might have heard of the model called GPT-3. So this model has 175 billion parameters. So if we wanted to actually do inference of this particular model, we'd actually need 350 gigabytes of HBM memory, right? Which is not actually available on any accelerator or device today. So in that regard, LLM inference are kind of similar because they're both multi-device workloads these days. So when we built Inferentia 2-based inference optimized instances, we took that into consideration, and we actually designed a fast chip-to-chip interconnect that can actually sustain 10 terabytes a second across an instance. And this enables our customers to run a single model of more than 200 billion parameters on a single instance. Inf2 is actually the only inference optimized instance available today that has such chip-to-chip interconnect, and it makes it highly optimized for LLM deployments. So we've packaged it in a cost-effective way, and this gives our customers capabilities that only exist in training-optimized platforms.
Right. So, you know, without Inf2, customers would be forced to use these training-optimized instances that are not cost-optimized for inference. And as we said, you know, your inference costs can start to skyrocket in that case. And developers are forced to do this like performance versus cost trade-off. But with Inf2, you can get the real-time performance you want while keeping the costs under control. What are some of the other ways to optimize LLM inference?
Yeah, so there are some emerging best practice nowadays for doing LLM inference. So for example, in inference, we generate 1 word or token at a time, which actually makes the model memory bound in most cases. And we've actually got several different ways that we can deal with this effectively. So we use techniques such as key value caching, quantization, and also memory compression. So let's dive into these, starting with key value caching, or KV caching for short. So this is a relatively simple idea, but it's actually quite powerful. So when we're predicting the next word or token in a sequence, we actually identify parts of the computation that are repeated. So instead of redoing this computation, we actually cache the intermediate results on every word, and we reuse them for the next word. So beyond that, we're actually optionally applying quantization techniques, which is where we run the inference at a lower precision, such as int8, and this achieves higher memory and compute efficiency. And we can even go further. We also use deeply embedded general-purpose vector processors inside the Inferentia 2 compute units, and these have direct access to other parts of the hardware as in their caches. And these vector processors can also run user-defined C++ operators. So customers can bring their code and they can innovate even further to drive performance to much better level. So using techniques such as, say, 4-bit quantization, memory decompression, or any other novel idea.
Yeah, you know, that ability to run their custom operators efficiently is so critical for this field that is moving, and you know, developers are innovating so fast. We have, of course, built Inferentia and Trainium for the sort of state-of-the-art deep learning, But because this field moves so fast and developers want to push the boundaries and, say, improve performance or the model expressiveness, that ability to run custom operators in a very efficient manner is just awesome. Now, we have talked about so many innovations today about the silicon as well as the servers. And we heard from NAFA this morning. And one of the things that NAFA says, especially to the Annapurna team, is that don't be chip heads. And what he means by chip heads is don't be people who are just focused on innovating on the chip level and sort of packing in all of this innovation. That's important. But also think about the customer experience. What is the end user experience like? And so can you talk to us a little bit about what we've done to ensure a seamless user experience?
Sure. So the first thing is that it's really simple to get started, right? So we've built the software called the Neuron SDK. So this provides the glue essentially between the ML framework, such as PyTorch, where our customers are developing, and our purpose-built accelerators. So most customers can just bring their existing training or inference scripts, and with minimum changes, it'll just work directly on our hardware. So we recommend that customers check out our documentation, where we actually provide a number of tutorials and getting started guides, including examples for pre-training and fine-tuning LLMs using AWS Trainium, and also deploying models to Inferentia 2. We also provide tutorials for compiling and deploying Stable Diffusion models, like the example you saw today. So all you need to do is just search for AWS Neuron SDK, and it should take you straight to our documentation. So if you're using the Hugging Face Transformers library to train and deploy deep learning models, then we actually recommend checking out a new library that we've been developing in conjunction with Hugging Face called Optimum Neuron. So this library provides an optimized version of the popular Transformers library for our purpose-built ML accelerators. So just search for Hugging Face Optimum Neuron, and it should take you right to the GitHub and documentation pages.
Awesome. Well, thank you so much for that insightful conversation, Matt. And thank you to the audience for joining us and tuning into this segment.